Hello. Okay, so this mic is awful. I don't know why my mic isn't connecting. This mic. So you guys can hear me fine? Because this mic is kind of really bad, but I don't know why my main mic isn't connecting. So we're gonna start over then. Yeah. I don't know why. I have a Yeti here. And the cord's really finicky. I guess the cord's not working. The webcam that I'm using right now is the default webcam on my laptop, which kind of sucks, but it's better than you guys not hearing me at all. So we're gonna start over here. If you didn't hear me before, well, yeah, you obviously didn't hear me before. I'm a biophysics student at Clemson, which means I use physics to solve biological problems, which means that we're basically looking at the intersection of physics and chemistry and biology. So we're looking at the chemistry at a very fundamental level. So this whole net ionic equation thing is very important, and especially my discipline and every discipline. That has to do with chemistry. So the whole motivation of a net ionic equation is we're essentially emitting the parts of the chemical that don't really do anything. So we have to start from sort of the basis of a molecular equation. And the molecular equation that I wrote down was the classic forming table salt and water, two things that are very edible, out of two things that are very toxic, sodium hydroxide and hydrochloric acid. And one of those I've actually gotten in my mouth before. So since this stream is really tiny, I can sort of center this around you three. So you guys are very encouraged to ask questions. You don't have to be shy, because that's kind of the whole point of this kind of environment, is that you can interact with another student that was learning this very recently. So we good? You guys are all caught up? You guys still here? Hello? Or is the mic just that bad? Let me see if I can, okay. Yeah, so my Yeti is just straight up not connecting anymore, so I'm going to have to get a new cord for that. So we have to look back at solubility and what things are soluble in water. And there's a whole table of solubility rules that people in AP Chem are often encouraged to memorize, and I think that's stupid. And I hope you guys agree with me that it's just kind of stupid, like to just memorize that big table. You're not really learning anything. So my chemistry teacher last year, my AP Chem teacher last year, came up with a great, very catchy rhythm almost. Anything with potassium, sodium, ammonium, and nitrate are all soluble, and that'll get you good enough, or that'll get you a sufficient amount of questions answered on the AP exam. So potassium, sodium, ammonium, and nitrate are all soluble, and also the strong acids are soluble. That's kind of the definition of a strong acid, right? The definition of a strong acid is, we'll say HA, just generalizing it to any anion dissolving in water. Produces its ions completely. This is the definition of a strong acid. So strong acid. You might see this written a little differently. HA plus H2O, I think. Yeah. Producing A minus, or H3O plus rather, plus A minus. These two are equivalent, almost intuitively equivalent. So any strong acid is soluble, including hydrosulfuric acid or sulfuric acid. I cannot talk. Hydrobromic acid, hydrochloric acid, all the strong acids that you should remember from your acid-base unit. So we're going to look now at a net ionic equation and how we motivate it. Or rather, we'll look at a complete equation. I never use this vocabulary when talking about my AP class, but complete equation is essentially you separate everything that can be separated to extract more information out of it. So when we're looking at this, is the sodium hydroxide soluble? What do you guys think? Is the NaOH soluble in water? Throw a guess out there if you're not confident with your answer. Is the NaOH soluble in water? Yeah, it is. Any potassium, sodium, ammonium, and nitrate are soluble, and that species has sodium. I'll try and talk a little slower just for the case of the bad mic. So we have NaOH dissolving into its ions, Na plus plus OH minus. So the whole idea with a complete equation is you could substitute almost algebraically this for this. And in the same case, we have HCl, which is probably the most famous strong acid, H plus plus Cl minus. We can substitute this in for this. And substituting that into the molecular equation we have up top, this becomes Na plus OH minus plus H plus Cl minus produces, well, first there's the H2O term, there's the water term. And is the sodium chloride soluble in water? What do you guys think? Yeah, it is. There's the sodium, potassium, sodium, ammonium, and nitrate rule that I talked about earlier, and it's also kind of intuitive, right? If you think about like NaCl is just table salt, you can definitely dissolve table salt in water. I'm sure when people, or at least when I was a kid, but I was a weird kid, but I was a kid, I'd dissolve table salt in water and drink it. Tasted good. But yeah, that also works. So now we have plus Na plus Cl minus, and we can flip around this. We can flip around these terms. We did that down here. You can flip around the terms just by algebra rules and summing rules. So this is the complete equation. This is what this is. This is what this means. The complete equation here is we have sodium ions, hydroxide ions, hydrogen ions, and chloride ions reacting to form water, sodium ions, and chloride ions. And what do you guys see intuitively about both sides of the equation? We're thinking about it algebraically. There's a neat little thing we can do here that sort of omits terms. What do you guys think we can do? We can subtract terms on both sides, right? So it's almost like, and this is what a net ionic equation is. This is what is defined as a net ionic equation. So when we're looking at this down here, we can subtract Na plus on both sides. And we can also subtract a Cl minus on both sides. And that will give us OH minus, or rather, I'll write out the full thing. We have Na plus Cl minus plus H plus Cl minus, or rather plus OH minus. I sort of messed with the terms there, but it ended up, it's going to end up looking more intuitive anyways. Forms H2O plus NaCl, or Na plus Cl minus. And when we subtract it on both sides, this goes away, this goes away, that goes away, that goes away. And our net ionic equation is just a simple H plus OH minus yields water. Does that make sense, guys? Was that clearly defined for you two? Let's say you three, but someone left the stream. That's just how a net ionic equation is defined. The net is sort of like is indicating summation or subtraction. So we have the molecular equation up there, right? And then when you go from molecular equation to complete equation, we're splitting up the ions that are soluble. We're splitting up the compounds that are soluble into their ions. The net ionic equation there, it becomes a net ionic equation when the similar terms on both sides are canceled. So if we think about like an algebraic equation, we're going to make this look a little different. So let's say we'll say Na plus is A for sake of an algebra argument, and OH minus is B. The H plus is a C, and the Cl is a D. And we'll replace the arrow with an equal sign. And this gives us water, which is a new species, and we'll say that species is BC, combining the OH and the H, plus Na, which was A, plus Cl, which was D. And do you see that you can sort of get rid of the A and the D on both sides? Yeah, so that's kind of just the same case there. AD goes away, AD, you get B plus C equaling BC. And that's sort of the same case here. And when you cancel the ions on both sides, that's sort of like working with the summation. And if you think of like what net is, like net effect of something, like if I pull something this way and pull something this way, the net effect is it stays still. So it's sort of like two things canceling, and when we look at the complete equation, we're canceling things on both sides. So it becomes a net ionic equation, and that's how the net ionic equation is defined, because you're taking the net of the ions in the chemical reaction. Does that make sense? Awesome, cool. So this result is very significant. It turns out you can generalize this with any strong acid and strong base, so I'm going to show that. So a strong acid is defined by a certain chemical equation. Strong acid is defined by the following chemical equation. HA, I'll ignore the water term. Just know this is happening in water. So that's how a strong acid is defined. We mentioned that earlier. An acid dissolving into an anion and a hydrogen ion, and then a strong base. Strong base is defined as the following. It's defined to be how should we define a base here? We're gonna look up how it's defined, because I have a good idea of it, but I can't really put it into intuitive terms. Well, actually, the strong base could just be defined this way. The strong base can be defined as BOH, that's better, dissolves into B plus OH minus. So that's how we're going to define that. Hey Sonia, you just run the stream. Sorry, my mic's bad. My Yeti kind of just stopped working, and I'd have to reset the stream to change the mic. Well, I wouldn't have to, but otherwise it would be a pain. So what happens with a strong acid plus a strong base? This is basically a double displacement reaction. if you remember how a double displacement reaction is characterized. The A replaces the A and the OH kind of switch places. So we have HOH plus AB, or rather BA, just to stay consistent. And if we think about the Lewis structure of HOH, it would just look like that. And this is also very clearly just normal water. So we have HA plus BOH turning into BA plus H2O. There's more vocab to discuss here. This would be an acid, strong acid. This would be a base. This would be the salt or the precipitate. Either one works. Salt is more commonly used in an acid-base reaction like this. Precipitate is more used for something else that we'll go over later in the stream. So this is a salt. And this is just water. There's no special name for it in this case. If the water were under the arrow, it would be called a solvent. But in this case, it's a water, just because it's a chemical species in the reaction. So the reason why we define strong acid and strong base earlier up here is because we're going to substitute this in for this, and the same case for the other one. So we have H plus A minus plus B plus OH minus turning into. So here's the kind of predicament with the salt here. This is usually soluble. I can't say it's always soluble, but it's almost always soluble, just by the rules of an acid and a base. If it's going to dissolve, it's almost more than likely to dissolve as salt, because that means that this B and this A already have weak bonds with their hydrogen, so there's no reason they should have strong bonds with each other. But we'll just keep it like this for now. B plus A minus plus H2O. And the reason why the H2O isn't split into terms is because it's not soluble in water. It is a little bit, and you'll learn about that later, but it has a very very weak ionization constant, which you'll learn later when you go to equilibrium, which I think is my favorite part of chemistry. But now this cancels with that, and this cancels with that, and we get, as expected, H plus OH minus turning into water. So yeah, now we've generalized what happens with a strong acid and a strong base reacting together. Does that make sense? Strong base and strong acid. Yeah, but you have to make a distinction there. When we're thinking about a strong acid and a strong base, it's not necessarily it's not the entire acid reacting. It's just the hydrogen part of the acid. And same goes for the base. It's not the entire base reacting. It's the hydroxide part of the base, the OH. And that's the whole point of the net ionic equation, is we're emitting the parts of the acids and bases that don't actually react with anything. Does that make sense? Yeah, okay, cool. So the next one would be a normal precipitate reaction. And I did have an example, but the stream kind of happened to got caught up on my stuff. So this one this is gonna be a complicated reaction. We have, what color should I do this? And I'll do it in orange. We have 3 of this complicated molecule, NH4,2CO3. And when we're looking at these complicated things, we have to define their states of matter. So this is aqueous. When we were looking at the strong acid and strong base reaction, an acid is aqueous by definition, so you don't really have to deal with that, just because it's aqueous by definition. A strong acid is a compound solid compound that you can dissolve in water, and it becomes ions, or rather, it becomes aqueous. It splits and it loses its bonds, so it becomes aqueous in water. But now we have to define the states of matter, and this reacts with two. Actually, I'm not going to include the coefficients. This would be a balancing exercise. NH4 2 CO3 aqueous plus Al NO3 3, and that's also aqueous. So these are complicated chemical species, but what we're going to do is we're going to try to set up a net ionic equation for this situation. We have two aqueous species and we put them together, and what happens? So the first thing we need to do is think about what actually happens in the reaction. So what happens is a double displacement reaction. So essentially, do bright green. Essentially, these and these switch. And the two compounds that we end up getting are, I'll draw it down here first. We get an aluminum combined with a carbonate, and the aluminum has a +3 charge, combining with a carbonate. And I think the CO3, the carbonate ion, has a negative charge. I'm almost sure it has a negative charge. No, it has a negative charge, actually. Well, I'm the idiot. And that's the first one. And then the second one would be an NH4. Yeah, because an NH4 has a plus charge. And then an NO3 minus. So these are bonded together, and these are also bonded together. But the reason why they're not written as chemical species is because they're not balanced yet. I haven't balanced their charges. Does it make sense where I got these two combinations of atoms? Or rather molecules, not atoms. Ions would be a better word, actually. So what we have to do is we have to cross their charges to get something that's a neutral compound. So this is Al2, CO3, 3, right? You bring down this, and then you bring down that to the front. And then this is, it's already a positive and a negative charge. Yeah, this is the double displacement, yeah. You could call it double replacement. Double displacement is a term that is more commonly used, but it's a double replacement reaction. That also works, I think. And this is NH4, NO3. So now we have some terms to write. We have an Al2, CO3, 3 plus, and I'm leaving space on purpose so we can balance the equation, NH4, NO3. So we have to balance stuff. How do we balance this reaction? What should we start with? We should, well, there's only one aluminum on both sides. So we should balance the aluminums. So there's two aluminums on this side, and there's only one aluminum on this side, so we're going to double the amounts of aluminum on this side to balance it. But now we have 6 carbonates, so we have to do this to, or now we have 6 nitrates rather, so we have to put the 6 there. And then now we have 6 of these, so we have to have 6 NH4s on this side, 6 ammoniums on this side, so we'll make that a 3 because there's already 2 ammoniums. And we'll check if this is balanced. So we have, write it up here, 6 NH4, 3 carbonates, the charges, 2 aluminums, 6 nitrates. This is a 3 plus. Yeah, so, and there's also 2 aluminums, 3 carbonates, 6 NH4s, and 6 nitrates. And it works out. There's 2 aluminums on each side. There's 3 carbonates on each side. There's 6 ammoniums on each side and 6 nitrates on each side. So the balancing worked. So we have to now define states of matter for this. So typically, you'll be given the states of matter for this kind of stuff. This is a solid. Well, it kind of already makes sense, right? Like, which of these species is soluble? According to the rule that I gave earlier. On the right side, which one of these is soluble? The product side of the reaction. Yeah, the one with the NH4. Potassium, sodium, ammonium, and nitrate. There's 2 reasons it's a soluble. There's an ammonium and a nitrate. So this is aqueous. And this is where talking about things kind of, or not memorizing your solubility rules kind of screws you up, but it's safe to assume that this is a solid. And it actually is a solid by experiment. But if it doesn't have potassium, sodium, ammonium, or nitrate, it's safe to assume that it's a solid. So now we're going to work with the net ionic equation here. I'm going to do this so we can actually. So we need to split things up into their ions. So what are both one of them or neither soluble on the reactant side? What do you think? Are both of the reactants, neither of the reactants, or only one of the reactants soluble in water? Will they split into their ions? No, they're both soluble. They're both soluble. So when we think about potassium, sodium, ammonium, and nitrate, let's look at the first compound. Is there potassium, sodium, ammonium, or nitrate in that compound? Yeah, the NH4 is ammonium. This is just one of the ions you might have to memorize, the NH4. This is ammonium. Ammonium. This equal sign with the triangle above it, that triangle is a capital letter Greek delta. And the delta being defined, so this means it's defined as ammonium. So this does have ammonium, so this is soluble. And this has a nitrate, so it's also soluble. So we established that this is soluble, and we established that all 3 of these are soluble. So we're going to go to the complete equation and split them up into their ions. So what we need to do here is we need to look at the coefficients and think about how many are in the product side, or the reactant side rather. And there's 6 ammonium ions, 6 NH4+, and this is because there's already 2 in the compound, and there's 3 compounds, so there's 6 of them. And there's also 3 carbonates, CO3 2-, 2 aluminums, and then 6 nitrates. And then this turns into, the salt's not going to split up. The salt is a solid just by, it doesn't have potassium, sodium, ammonium, nor nitrate in it. So that's just Al2, CO3, 3, it's a solid. And then this aqueous thing that we have here at the end of the term is going to split up in solution. So that's 6 NH4 plus 6 NO3 minus, 6 nitrates. And you might be wondering why we don't include the state of matter of the ions. And again, it's implied. Something's not going to exist as an ion usually unless it's in water. You might see ionic gas, but ionic gas neutralizes pretty quickly with the gas around it. So, you know, there's no reason it wouldn't be an aqueous or aqueous species. And I might go a little more, or I will definitely go more in depth with that when we find this. So there's 6 ammoniums on both sides that cancel, 6 nitrates that cancel on both sides, and we get 3 carbonate ions plus 2 aluminum ions, forming this precipitate, Al2CO3 solid. So now we have our net ionic equation. Does that make sense? If it doesn't, just point something out specific and I could talk about it a little more. Okay, cool. So we're going to talk about why why something has a charge. It's implied that it's aqueous. So let's think about well, a solid isn't going to be charged. A solid is going to, if we have a charged solid, let's say we have, I don't know, a solid plate of aluminum, and this aluminum, or rather this is Al3+. What's in the air? What's in our atmosphere? There's H2, or not H2. H2 is not very prevalent in our atmosphere. There's O2, N2, a bunch of more. Well, there's actually some. I'll put argon because I think that's a cool thing to write down. There's argon gas. And these all have open electrons, right? This O, structure of O2. I think it's a double bond. Yeah, it's a double bond. So we're going to hold on. Yeah, just verifying. It's a double bond. So there goes my phone. So this is a double bond between the oxygens, and this is a triple bond, and this is argon with, these aren't really lone pairs, but they're definitely around the molecule, and this is could be a pretty strong attraction, right? It's a +3 charge. This is a pretty large charge. So you can be having, this this double bond attracting, this triple bond attracting, because that triple bond is electron rich. That double bond is electron rich, so it has sort of a negative charge, but not really. These electrons can combine here, and this aluminum is going to become essentially neutral. There's going to be negative species bonded, or not bonded, but there's going to be an attraction between negative species and positive species, which positive plus negative is going to come out to about 0. So a solid aluminum with a charge it's not very coherent. I'll make that very clear. Solids won't have charge. Won't have charge. And it's sort of the same case for a gas. If we think about, again, what's something we can think of? We can think of H+. Well, imagine this can exist in gaseous form. What else is in the atmosphere again? It's also oxygen, double bond, oxygen, nitrogen, triple bond nitrogen, and then we have argon again. With the electrons, we'll denote that with a circle. Again, this can attack, and then this can attack as well. But there's no reason that that'll be positively charged for the same case. Yeah, same reason. The more accurate reason is that when it's in ionic form, there's free electrons, but when things are bonded together ionically, there's those electrons are not they're not free electrons. They're stuck. They're rigid in one spot. But when it's an ion, the electrons are free to move around the atom, and that's exactly what electric current is, right? If we have a wire. what electricity really is, it's just electrons moving through the wire. And the electrons can't move. The electrons can't move in the solid. So, but the electrons can move in an aqueous solution because the ions are free to move around. But when we think about something like the next question is, well, why does it happen if it's in water? And the reason why is water is polar. And we'll talk a little more about that. So if we think of, again, Al3 plus and water. What do you know? What do you know about polar bonds? There's a partial negative charge on the hydrogen or on the oxygen, or not the on the oxygen. There's a partial negative charge because this bond is polar. It has a partial negative here, and a partial positive here. So there's an ionic attraction here. However, in the case of the solid in free atmosphere, it's a bunch of compounds attacking the aluminum. That doesn't really form a specific chemical or a specific species, and it's the same case with the hydrogen in gas, or the gaseous hydrogen ion. It's a bunch of species attacking the hydrogen, but when we're talking about water, a single solvent, it's literally just a single solvent attacking it. So you can sort of omit the water, because although the water, what would be a more accurate term in the thing here, and this would be, we're talking about the reaction, we could sort of write a bond. So this is kind of the true chemical species in this formula down here. But the water doesn't react. The water just attracts to it. So we don't talk about the water, and also it's just kind of pointless to talk about. So it can exist in it can exist in water. So that's why when there's something on a charge, when the charge is on something, it kind of implies it's aqueous. So what else do I have for you? Actually, we're gonna look, because I'm not really sure what else I can talk about. So yeah, the solubility rules, balancing complete ionic reaction, spectator ions. So a spectator ion, we're going to be defining that is literally just an ion that watches. It's an ion that's in the solution but doesn't really react. So it's the ions that we cancel out here. So I'm going to go back to the simpler example and also expand my canvas a little bit. We have Na plus Cl minus plus H plus OH minus, that's an awful O, yielding water plus Na plus Cl minus. So what do you think the spectator ions are? The ions that are watching. Exactly what spectator means. Well, what would make the most sense for that term to be defined as? Yeah, all the ions that were crossed out. And that literally means from the term spectator. Spectator is something that is there, but it's not participating, which is exactly the kind of analogy that's here. So spectator ion, spectator ion, spectator ion, spectator ion. And often it won't be that spelled out for you. Often you'll see hydrobromic acid plus potassium hydroxide forms. First, you'd be asked, like on an FRQ, for example, you'd be asked, what's formed? And then find the net ionic equation. And then what are the spectator ions? So what's the no, they won't. You're completely right. They won't react. It's kind of a bad, by definition of react. Yeah, react just means a rearrangement of atoms. And when we're looking at rearrangement, they're not really being rearranged at all. They're just kind of floating around in solution. In terms of they're still doing chemistry. It's just they're not reacting. Does that make sense? Yeah, so hopefully this is a little bit of an easy question. So when we look at HBr plus potassium hydroxide, what's formed? You should get a salt and a water. Yeah, KBr plus H2O. And the net ionic equation? It's a strong acid and strong base reacting together. No, the net ionic equation, it wouldn't be the spectator ions, it would be the hydroxide and the hydrogen. It's the same thing as before. This net ionic equation is something you kind of should be memorizing for strong acids and strong bases. So it would be the same as the one before. And then the spectator ions are what? We pinged on Discord. Sorry about that. Yeah, you're right. One quick little note: if you don't put a charge on something, you'll get points taken off. But I'm not expecting you to put a charge in a chat. That's kind of stupid. So we're gonna work this out. It's just double displacement reaction. So this will get you. We'll put the states of matter on, just to be a little more rigorous. So this forms H2O, and this is a liquid. Liquid and aqueous are different things. An aqueous thing is something dissolved in the liquid, and H2O is the liquid, which should be the H2O being the liquid shouldn't be the big surprise. And KBr, and you have to find out if this is solid or aqueous, and it is aqueous. It has a potassium in it. So that's that. To complete the equation, the net ionic equation is simply strong acid and strong base reacting together. So it's the same cookie cutter reaction as always. H plus OH minus forming liquid water. And then the spectator ions are K plus and Br minus. So that's that. Definitely not the ions. Like I said before, the ions are, it's implied the ions are aqueous, but if the thing is solid, like in the case of the complicated chemical equation here, the solid on this species matters. It matters a lot. Because if the solid indicates that you know it's staying as a solid and not dissolving again. Does that make sense? Yeah. So if there's a charge on it, it's implied that it's ionic, that it's an ion. So another example I can break out. Yeah, redox. We haven't done redox. So let's do the next kind of reaction that involves a net ionic equation. This is called a redox. So we're going to look at an example. Solid zinc plus CuSO4 and this is aqueous, forming Zn4. This is aqueous plus solid copper. So there's a quick note. So a lot of these things you're going to have to figure out the state of matter based off of the potassium, sodium, ammonium, and nitrate rule. However, if you see an equation like this and you see the aqueous next to it, aqueous means it's dissolved. So if it's aqueous, you can assume that it's dissolvable, that it's soluble in water. So the equation that we end up having, so this is the molecular equation. We'll look at the complete equation. We'll omit the vowels. So zinc can't really dissolve into anything. There's nothing with it. The copper can dissolve. This can dissolve. That's sulfate. Did I get the ion charges right? my phone go? There it is. Found it. Let's hope I got the charges right. So 4. Yeah, it's -2. And this is forming another aqueous compound. Zn2 plus SO4 2 minus plus solid copper. So what's the spectator ion here? What do you think the spectator ion is in this equation? No, it's just the SO4. The zinc and the copper aren't ions; they're solid species. So when we think about spectator ions, well, you are right in that they are ions. No, the solids do not cancel out, because the solids, like the reaction here is sort of if we're looking at just what happens to the copper, you're on the right track. Honestly, I think you have a good intuitive understanding. We have the Cu2 plus forming, or rather, I'll leave the arrow here. Solid copper, and what got added here is 2 electrons, right? Something with the +2 charge turning into the same thing with the neutral charge. You have to add electrons to it, so it's turning into a different species. So while you are right, there's coppers on both sides. The copper is turning into something. It's turning into a different kind of copper. Does that make sense? Yeah. Okay. Cool. So the SO4 goes away, and now we have the net ionic equation, or rather, I'll say EQ instead of Q. Net ionic equation is solid zinc plus the copper ion turning into the zinc ion plus the solid copper ion. So what's actually happening here? It's zinc losing 2 electrons. Yeah. And I can actually go over something cool about that. So when we're looking at what happens to the zinc, we have the zinc losing 2 electrons. And we look what happens to copper. We have copper plus Cu solid copper forming into, or rather, that's not copper. It's 2 electrons turning into solid copper. And what happens when we add these reactions together? We get, from the first one, solid zinc plus copper ion plus 2 electrons forming the zinc 2 plus 2 electrons plus solid zinc. And what can we do? What can we cancel out? Yeah, we cancel out the electrons. The electrons actually don't even really do anything in the overall macroscopic state of things. So this and this are equivalent. So there's 2 different ways to look at it. There's the net ionic way, and there's also the whole metal losing electrons. Good on you for catching the zinc losing the 2 electrons. That's good. That means you understand this stuff pretty well. So there's another strange way to do this kind of stuff, and you'll get into this. Let's see. I'm going to look at the schedule whenever. Thermodynamics. Okay, yeah, so applications of thermodynamics. There's no date on the spreadsheet that we used for our streams, but that's the second to last unit. The last unit is review. And you get into that kind of stuff more in depth with the metal losing electrons and another metal gaining electrons. It's called an anode and a cathode. And you actually learn about batteries towards the end of the year, which is really cool. That was one of my favorite units. It's called electrochemistry. You can look it up now if you want. You'll be able to understand most of it, except for the thermodynamic stuff and the spontaneity stuff of it. But yeah, so do you have any questions at all? I can go over stuff again. I can really spend as long as I want helping you out. Since you're the only one here, I can really center this around you. Do that. Get a full picture. Anything at all? Yeah, okay. So top right. So what I was explaining here is why something with a charge implies that it's aqueous. So what would happen with a solid that has a positive charge? There's an atmosphere. It's existing in an atmosphere. If it's solid just on Earth. And in the atmosphere, there's two of the most prominent chemicals are oxygen and nitrogen, and those exist as diatomic gases. So the oxygen gas exists as an oxygen bond to an oxygen with a double bond between the oxygens. And the double bond is electron rich, right? That's kind of what a double bond is. There's a lot of electrons in the double bond. So it can sort of act as something called a nucleophile, which means that it will attack electron rich. It just means a lot of electrons in that one region. So a double bond, this maybe make it more obvious. There's one bonding pair of electrons and there's another bonding pair of electrons. So there's 4 electrons in that region. Does that make sense? Okay, so that region can generally be seen as negatively charged. And when we have a solid plate of really any metal with any charge, that Q just being any positive number, or rather, yeah, that Q being any positive number, that negatively charged region can sort of attack the metal, which makes it effectively neutral. And in the same case with nitrogen, there's 3 bonding pairs, so it's even more electron rich in that region, and that can also attack the species and make it effectively neutral. Does the solid part make sense? It's just opposites attracts, pretty much, in a nutshell. What's confusing? So the oxygen there's an electron-rich region in the oxygen, and that'll attack anything with a positive charge because the electron-rich region is negatively charged, and opposite attract, so the positively charged metal is going to be attracted to the negatively charged electron-rich region. And in the same case with the nitrogen, there's an even more electron-rich region in the triple bond, which can attack the positively charged metal as well. Yeah, okay, cool. So, and it's the same case with a gas. A gas is going to exist around other gases. So, for the same reason, there's multiple gaseous species around the other gas that we're looking at that can attack that ion for the same reason. Does that make sense? Yeah, okay. And the reason why that it's the exception is the aqueous is because when we're looking at the gas and the solid, there's multiple different chemicals attacking the positively charged metal. However, in terms of like aqueous aluminum and water right here, so this term right here is what I'm explaining. The water looks like this, right? And water is a polar molecule, so there's a partial negative charge on the oxygen. Partial positive, partial positive. So the electron-rich region is at the oxygen, and that will attack the aluminum just because opposites attract. And the reason why the aqueous is the exception is because in the water, there's essentially only water. So that means that the the chemistry is still the same because there's only water on both sides. The environment is water on both sides. So when we're looking at like any just sort of physical process, we have AB and the environment is water, turning into A plus B minus plus H2O. So it's the same environment on both sides. And because the environment is the same on both sides, we can sort of cancel it out, act like it's not really doing anything. However, in the case of a solid and a gaseous ion, it's not the same environment. There's different different chemicals interacting with the metal. Does that make sense? You're good. You got it right. Yeah. Yeah, you're completely right. Yeah, cool. Do you have anything else? Anything else you want to get clarified? Okay, cool. So for both you and people watching the replay afterwards, I have an Instagram. You can send me questions for pretty much any STEM class you have, AP, honors, whatever. If only I could spell correctly, that'd be great. This is my Instagram. You can DM me questions anytime, and I'll answer them as soon as I can. And yeah, of course. Don't feel like you're being a burden if you want to ask me questions. It's literally my job. So yeah, Stephen, have a good night. Thank you for tuning in the stream. I'll be streaming next Thursday, chemistry as well, I think. I can check that. If not, then yeah, I'm not streaming next Thursday, but I will be streaming the Thursday after that, probably. Have a good night. People watching the replay, take it easy, and hope you guys learned something. Take it easy.